because I have two screens, and that's the main reason why I don't use the full screen in PowerPoint, because it's going to be, I mean, it's unclear what's going on, right? Plus, I'm going to turn my camera off, so I don't have to get confused myself when I'm looking straight forward at you, right, on the screen on the left. All right, so let's recap what we did last time. Okay, a few comments. So the second lecture, right? So speaking of lectures, right? When I click my Finder, then that's the again, that's the folder, Dropbox folder that we shared. I added up a new file. It's called a new folder. It's called Java. Over here, we're going to use it today, and these are two PDFs: today's lecture, lecture number 2, and the first lecture. And then we're going to go over these M files today too, right? And okay, that should be it for now. So I'm going to move it to the left. I do, so that's the structure of the folder that we share. As I said, I added up extra file. It's called Java. If you have a Java installed on your laptop, on your computer, if you don't have it, just go to oracle.com and then download Java so you can run that script. It's very helpful to illustrate some systems in the plane. It's easy breezy, right? You just click, and you will see how it works. I'll show it to you later today. Okay, so I still advise that, again, in PDF, you can get these links, right, and then watch the movies. They're very helpful. I mean, again, they're very helpful. They tell you the story how spikes are generated, some kind of simple biophysics, nothing really special. And then given that we live in the 21st century, right, and we all have, brains and so forth, so it would be very not selfish to know whereabouts how our neural systems circulates. I mean, again, and functions, and what are called misfunctions, right? Why all of a sudden we can't remember things, right? How we learn certain rhythmic outcomes, that's called locomotion. That's what I'm interested in. And then I just forwarded a link to Alexia Lusha about it's a brand new institute. So I guess you all know Microsoft and Bill Gates, and he had a long-term partner or a long-term co-investor, and his name is Paul Allen, and Paul Allen founded, it's called Paul Allen Brain Institute in Seattle, and at the end of November, he also founded another institute, Paul Allen Institute of Neuronal Dynamics. So it's mostly run by neurophysiologists, right, and neuroscientists, but they have what's called a dire need for people who know computers, modeling, and how the neural system operates, right, at a certain level. So the idea that they're trying to figure out how the brain of a mouse is designed, right, and at the very high level, resolution of intracellular recording, and then an imaging, calcium imaging, and so forth, and on. So they're amazing. And again, given that Allen invested tons of money, right, the outcome is really, really amazing. You're welcome to Google. One more time, it's called Paul Allen Brain Institute in Seattle. Really, really amazing what they've done over the last years. And these are programs here in the States. It's called Brain Initiative. It's very similar to what Obama administration launched. It was called Genome Project. And in Europe, they have European Commission also supports, relatively new. I mean, when I say relatively, it's like 4 or 5 years old already. Program in brain simulations. But in Europe, it's more on modeling part. Here, it's overall sort of joint venture on the brain studies. Okay, so I do suggest that you watch this movie. It's very interesting. Okay, so back to where we're starting point, integrating fire. I'm not a big fan of integrating fire, honestly, but it's a good starting point. Okay. Спасибо, Losha. Okay, I can see your email. So the reason why I'm not a big enthusiast of integrating fire, because again, this is what typically happens when mathematicians come into the field. They're trying to simplify things, and the simplification or reduction eventually results in whether it becomes unclear whether this what you see is an artifact. Okay, artifact means just a modeling flaw, or it's a real phenomenon. But anyway, okay, it's a good starting point. And today we're going to migrate to some more accurate Hodgkin has the type of models of cells plus what's called phenomenological models. Okay, and I'll give you some history of that. And the very first simplified Hodgkin-Huxley model was called Maurice-Lecard. We're going to talk about this, and then, all right. So what's the bottom line? Bottom line is that this is integrated fire neuron, right? It has a single differential equation, which means it can't show any curious dynamics other than exponential convergence or exponential divergence. And the idea is that, okay, then these are single current involved in this model, and it's called ohmic or Lie current. Okay, and Lie current basically means that voltage converges to some what's called rest potential, which is typical negative 65 millivolts. And whenever you apply an external current, then you make cell more excitable, right? You excite it, and that level negative 65 raises, right? So now that's your new target, the green line, and then you set up an artificial kind of threshold. It's not artificial, it's observed from experiment. So and whenever cell reaches the from below, it reaches this value negative 45, we say, these are a spike, right? Or we just say like bam, 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 bam. But we don't see spikes in the model because basically we set the voltage back to negative 65 or even lower, right? And then the story continues, right? So then voltage goes up again as long as spike is applied, and then you have now in this case 3 spikes and so forth and so on. So you can basically find analytically, if you want, when the cell reaches this level. Okay, and that's what you're supposed to see here. Again, this is just a simple file. This is called integrated file simple 1, which doesn't generate any spikes. But what I've done is that as soon as you get to the level of negative 25 or 20 here, just let me see, it should be on the right-hand side somewhere in the code, negative 20 threshold. Then it generates action potential, and then you reset it. So you're welcome to look at this file. Again, I hope that you have MATLAB installed on your laptop, okay, and it's freely available. I mean, here in the university, but again, it's not free, and the university must pay a license. It's called university-wide license. And I have no idea whether High School of Education have a license for MATLAB, but then they have a free licenses for students, I guess, right? So you should be able to register. So the idea is then if you increase the drive, the external current, then the spike frequency is going to go up, okay? So, but again, that's what basically integrated file can do. And then I showed you another file here. It's called integrated file simple periodic drive. It's nothing special, right? Basically what I've done is here, okay, so you can see on the right-hand side, this is just called Euler method of integration. This is the simplest integration method, or the solver algorithm, right? It converts the differential equation to a difference equation with a certain step. Make sure that this step dt is not large enough, relatively small. I mean, you can play with that. And plus you add, in the right-hand side, this periodic forcing. So as you can see, it has a cosine, omega, and then dt, basically. This is just omega is the frequency of periodic force. Okay, that I external is the amplitude of the periodic force. And what you see here is that, so you have a silent cell, okay, so this level, and then you apply a pulse, okay. You put cosine in heavy side is a step function between 0 and 1, okay, and then when you apply it, then your cell generate a number of action potentials, right? I mean, of course, you can change the drive, the frequency of the drive and the amplitude, and it's going to give you some kind of this bursting activity, right? That looks like a real bursting activity, which is typical, again, for networks. That what networks are supposed to generate during the locomotion of animals. And these are, I'll get back to this later on. So again, as I said, the integrated fire model is not supposed to generate nothing but spikes, that some tricky machinery, mathematical machinery, can be applied to adjust to add up another differential equation, basically to generate something like this, right? But I don't advise to do that, but it's just a matter of how mathematicians treat certain things. But I'll talk about this if you want. All right, so neurons are great, but again, neurons are useless unless there's a network, okay? And let's consider the very first network is called two cells, V1 and V2, and they're coupled by what you see here. It's called electrical synapse, or also known as a gap junction. So basically, the idea is that during the development, neurons, when the cell is small, not the cell is small, when with ganglion is a conglomerate of cells. When animal is small, their neurons are tightly packed in a ganglion, and sometimes what happens is the somas basically going to be very close to each other, right? So which means there's a current that is proportional to the difference in the voltages between cell 1 and cell number 2. So that's how the current is going to look like. So it's a V1 minus V2, provided that this current flows from cell number 1 into cell number 2. And G electric is the maximal conductance. Okay, and vice versa. So there's always interaction between the cells. And that's how we write down the equations. So the very first equation is going to look the standard form, and then you need an external current to make sure that the cell will generate action potential. And then you have plus G electric, V2 minus V1 in the first equation, and the reverse difference in a second equation. So that's basically it. Okay, and the question is what they can do. Okay. And the idea is that you still need external current. The idea is the following, that if the external current is non-present, cell is quiescent, we say it's a rest potential, and then you add up a current and it starts generating some spikes with a certain rate. And in his case, right, the rate is low, then it gets higher, and then gets higher, and then you have what's called typical dependence of the spike rate on external current. Okay, and the question is, what's going to happen if you have two cells, right, and they have different rates, and when they coupled, what's going to happen? For example, one has a higher rate, like a blue cell, and the green cell on the right has a lower rate, just a few spikes. I mean, not a few spikes, but the frequency is lower, or it's even quiescent. So basically, and then you have this gap junction, and it looks like basically it's like a swing, Coachella. So it depends on, you have a heavier fighter on the, sitter on the left, and lighter partner on the right. Okay, and it depends on the length of the swing, right, and also depends on the mass. So for example, if the green cell is very, very far on the left, okay, from this boundary, right, it's over here in a kind of in a potential well that corresponds to the quiescent state, right, and the spiking rate of the blue cell is lower, then very likely then the green cell, I mean, again, can dominate dynamics, right, and both cells will become quiet. Or it may happen that basically the blue cell on the left, it will try to pull up the green cell and make it spiking. Okay, I mean, simple calculations can show what you can do, but again, whether it's worth doing it analytically, it's not quite clear. So, but bottom line, the overall message is that depending on how far the cells are from the boundary, right, how intense the spiking rate in a blue cell, or how quiescent, how deep in a resting state the green cell, basically what averaging is going to do is going to average the spike frequency in both cells, right? So typically the green cells, or the electrical coupling, is needed to create kind of a double force, right? Rather than a single cell, but double force. Okay, so it creates some kind of subset of cells that all either fight together, right, or become quiescent together. So sometimes you needed to raise your voice, right? Because sometimes, I mean, again, like in a human society, one voice sometimes is not enough. So you need your you need like-minded people who will raise their voices along with yours, so they can be heard better. Okay, that's why gap junction is needed typically, right? Again, it basically it meant to synchronize the cells if the gap junction is strong enough. Of course, you can ask questions. Okay, what is strong enough means? And strong enough means basically that this interaction, typically, it shouldn't exceed 1/10, sometimes 1/20th of the voltage difference in the cells. That's typical what happens in the cell. Okay, and then we're going to move on, right? And let's consider again this two-cell network, and let's assume that we apply a certain current, so the cells spike, and we would like to figure out, okay, what happens when you kind of increase the interaction between the cells. You increase this G electric, okay, so the cells can hear each other better, okay, and the idea would be the following, right? Look at this. So this time you have a change the green into red, then say the blue cell fires, right, and followed by the spike or action potential in the red cell. Okay, and again, blue cell and red cell are both spiking cells, so that means this is rhythmic outcome. And what you do, you measure this delay, tau, between a spike initiation in the first cell, in the second cell, and then divide it by the period. This is the period, say, of the blue cell, of the red cell. And then you have this sequence of what's called phase lags or phase differences. So delta I stands for this phase difference between spike initiations in the cells, and then let you run. And you have multiple options, right? Option number 2, for example, as time progresses or the number of spikes increases, right? And coupling is relatively small, you will see that the phase difference between the cell as I goes to infinity, right? You don't want to say infinity here. Over some reasonable number of iterates, it converges to 0 or to 1. Again, by construction, when you define the phase difference, phase lag, it's defined what's called on modulo 1, which basically means that, like in this case, right, you see the difference between the cells goes to 0, which means it can be that the blue cell fires first, but it can be the other way around, that the red cell spikes first, right? Then the phase lag is going to converge to 1 or 0, depending on what cell you pick as a reference cell. In this case, I pick a blue cell as a reference cell. Or case number 2, simplest case, right? Then phase lag converges to 0.5 or 1/2, which basically illustrated over here, which means the cells spike in antiphase. Okay, so for example, you see I pick up in this example 2 cells firing relatively close to each other, and as time progresses, you can see that the phase difference goes to 1/2. Okay, whether in the previous case it goes to 0. Okay, so, and here's the deal, right? So to illustrate intuitively what happens, imagine this following situation. You have 2 magnets, blue and red, okay, and they are on a metal ring, and you put them in the magnetic field so that they're going to spin, they're going to rotate, right? And let's say, consider the following case, right? When you have you place the poles of the magnets so that you have a minus here and plus here. So no surprise. I mean, again, your intuition tells you that as they keep turning around, rotating, then these 2 magnets will get closer and closer. They will attract each other, right? So they will fire in phase, so to speak. Okay. But on the other hand, if I place the red magnet kind of on the left from the blue one with the same polarity, then they will converge to the same state, right? So they will fire together. Okay. But surprise is, okay, so guess what? If I have, right, imagine this, right? If I place this red magnet over here, then this minus and plus will try to get them closer. But on the other hand, that plus and minus on the left-hand side will also try to get them closer, right? Which means you have a no-win situation, right? Which means no force can beat the other one, right? The opposite. So which means that if you place accurately, carefully, the magnets on the opposite sides of this ring, right? Therefore, you will get anti-phase state, which can be which can be which can have a certain traction basin, right? So which means you have this kind of bistability situation. So this network, even though it looks like that, so it looks like it's a monostable, right? It converges to either 0, 1. The truth is that the network of two cells that are coupled electrically can be bistable, okay? So that's what I was trying to say. If you keep increasing, say, in the interaction, make this G leak stronger, then the synchronous state will be dominant over the anti-phase state. In this case, I showed it the other way around. Here it's shown that anti-phase state has a potential well that is deeper and stronger than the potential well that corresponds to the synchronous state. But it can be the other way around. Option number 2, for example, okay, if you place magnets in a different position so that you have polarity minus and minus here, so clearly they will try to repel each other, okay? But if you place the red magnet on the left, it's going to be a very similar situation. They'll try to repel, and they'll try to repel towards this state, which basically means that, again, synchronous state in this particular case, that it doesn't look like it's feasible, right? So the network rather would produce asynchronous state. So, and to get this case from this equation, all you need to do is to either, I mean, again, it's just kind of cheating, make this G electric negative, but again, G electric is a maximal conductance, so it shouldn't be negative, right? Or you reverse the position of these terms, right? You switch V2 and V1 in this equation and respectively in the first two, and you'll get this case, right? Right, and then you can run your network just to see what's going to happen, and hopefully we can do that. Okay, and I guess that's the next slide. Okay, and what you see here, so I'm looking at this file. It's called integrating fire realistic two cells electric phase lag. Okay, so that's your electric gap junction, right? And at this point, what I have here, I make this interaction. Again, this number at this point is kind of, you can't say what's strong, what's weak. Okay, let's just say that you need to make sure that this number is large enough to see some reasonable progression. Okay, in this particular case, okay, the progression is that I pick up two initial conditions, right? For the second cell, I pick the second initial condition randomly. So basically, I use what's called a random number generator here. Every time you click run, this number, right, is going to be between, I think it's between 0 and 1. So which means this is fixed. And if it's a 0, it's going to be negative 60. If it's 1, it's going to be plus 120. So I'm trying to use the whole range of initial conditions. And what you see typically, right, again, this is just, I integrate from 0 to 1000, and I just show the last 100. This window shows you what the phase lag is going to be. Okay, indeed, the number of iterates is longer, and you can see I started initially that cells are pretty close to each other, and as time progresses, or the number of spikes increases, this number of spikes, that curve, which is a phase lag, it converges to a value of 0.5, which means that's this electrically coupled network of two cells will produce anti-phase dynamics at this value. Okay, so you're welcome to again open up the file and play. I can do it for you later on today, and then you gradually increase this number, right? Just not this number, I mean G electric, and make it slightly stronger, and then you click run again. Okay, let me just do this so to illustrate, right? And let me just announce what's going to happen is that, and then you click 10 times out of 10, and then you will see something like this, and the phase difference will be something like that, right? It basically jumps immediately, right, to this value, and it stays constant, which means this cell spike together, okay, and the red cell precedes spike in a blue cell. So that's what 1 means. Otherwise, it's going to be 0. Okay, and what you do, I remove this file from the Dropbox. So what you can do, you can run it in cycle, gradually increasing this G electric, and then you try, say, 100 times, and you will see something that when G-electric is relatively weak, again, relatively weak, you're welcome to try to figure out what that means. You will see that typically you're going to have anti-phase or out-of-phase spiking in the cells, right? And then you keep increasing, and sometimes you will see in-phase spiking, and then you increase this G-electric, and then what's going to happen is that the number of trials when you see it out-of-phase spiking is going to drop down, and whereas the number of in-phase cases will grow, and there will be some intermediate value when the ratio is 50-50. So which means you have potential wells that are basically have the same depth, right, and the same width. Okay, so which means at this point the network is truly bistable. Okay, and that's how you determine what the what's the value of G-electric should be for your network, especially given that it depends also on an external current and other properties of the cell. So all I'm trying to say is that these numbers are all relative. Okay, so you better be it's like a bifurcation value. Okay, you better be G-electric should be less than that, middle value, right, or higher than that. Okay, and that's what we're going to see. Okay, and yes, what else I want to say that, so clearly if you make the coupling strength weak enough, right, then you won't see any progression whatsoever. If you start from, say, from this value, you'll see kind of plateau, which means nothing changes, right? In this case, you see, this basically means that the network jumps right onto these in-phase states almost immediately, right? It doesn't even converge to that value. Okay, so let me see. We are not in the rush. So what I do here, okay, let me find the windows that corresponds to this MATLAB. Okay, I click here. Up. Can you see the window? I guess yes. Okay, and then open up here, and then I click and I go to Integrated Fire and Integrated Fire Networks, and I click on Integrated Relays to Cell Electric Phase. Okay, this one. Okay, and let me see what I've got here. So every time, all you have to do is just set up the currents for the cell 7 and 7, okay, and G-electric, and I click Run, change the folder, and then I should get a window over here. Okay, so as you can see, let me just, no, not you, this and that, and then I put this back in the middle. Okay, you, and you over here, so I can better see what's going on. I need this window, this window. All right, now I can see it. All right, so that's my okay, this is G-electric is 2. Okay, I comment this out. You're welcome to change that. You run this. As you can see, I show only the 1/10 of the progression, and you can see that the phase difference converges to 0.5. Okay, let's do it again, run it. Okay, you see the slightly differential condition, but still converges to 0.5. Okay, do it again, 0.5, 0.5, okay, 0.5, 0.5, 0.5. Okay, so now if I make this number, say, stronger, 0.9, okay, click it, then, okay, what you see here, I mean, you can see that they're in phase, and when you see something like this zigzagging, that means the integration precision is not accurate enough, so there's a little phase lag over here, so which means it's jumping between 0 and 1, but it's pretty much the same. So if I do this again, oh, okay, you see now this network converges to anti-phase, which means, okay, it's truly bistable. So we have 1-1 score, okay, then 1-2, 2 stands for the anti-phase, okay, 1-3, 1-4, 1-5, 1-6, okay, 2-6, 2, 7, okay, 3, 7, 4. Right? But if I'm going to make it slightly stronger even more, right, and repeat the same experiments, okay, 0, 1, it's like a soccer, 1, 1, okay, 1, 2, 1, 3, 2, 3, and you keep running. So that's how we create what's called, in this use what's called Monte Carlo simulation, which basically use random initial conditions to evaluate in terms of probability what is known as effective potential wells. When people say, in physicists say effective, that means they're not real potential wells, right? It's just in terms of probability. So you can say likely I'm going to get in phase or out of phase interaction. It looks like, right, in phase still dominates, and then as soon as I make this number again 0.5 above certain threshold, okay, still in phase, surprise, surprise. Okay, anti-phase, in phase, and so forth and so on. But you got the point. And you can see that a little convergence, right? Just after 2 iterates, everything converges to in-phase state. So I'm going to stop here. And you may wonder why I need this. And the reason why I need this, okay, is that, again, simple neural networks, right? I'm not talking about brain at this point. They are in charge of determining the outcome. Okay, for example, like what's known as locomotion. Best examples, I mean, for the humans would be, again, breaststroke when you swim. Then the arms move in phase, right? When you switch to freestyle, then the phase difference, right? Your arms now move in an anti-phase, right? And the question is again, how do you pick the swimming style, right? I mean, of course, it's your brain, right, that picks it. But the big question that everybody keeps asking over and over again, right? Where is it in you? Okay, so your brain basically controls the locomotion, but where is that circuit in an animal that determines whether, for example, this dog, right, whether it's going to be bound to gallop different styles. So if you look at the bound, these are the front paws. So you see that synchronous in anti-phase with the rear paws. So it's going to be something like this flying together, and then swing, and then fire together again, right? And gallop, that means the animal lands on the left paw first, right? Then a little delay, phase difference, right? And so basically, it's going to be like cats. That's how they run. Okay, and this would be typical for the dogs and for the cats too. If they got scared, no, that's how they're gonna run. Okay, and then there are different other styles like trot when the dog walks slowly, right, and the cat walks. I mean, this walk. Yeah, so there are different styles. So that's basically you need to figure out what's the neural network organization architecture should be to produce these multiple rhythmic outcomes depending on a drive of external drive that is basically it's a descending command that originated in the brain and projected onto the network. And the big question is whether it's a single network that control all these locomotion types, or animals use different networks to produce different locomotion styles. But on the other hand, that means the brain should selectively pick up, say, okay, cell number 1, give me bound. Or now the drive, cell number 2, give me that gallop, right? But the truth is that in a primitive animals like sea slugs, brain is basically is a circuit that controls the locomotion, right? And the animals, either they can swim, they can crawl, they eat, right? And basically that's it. These are all functions that they can produce. Okay, and it's a big interesting question in the neuroscience, whether again the circuit is what's called multifunctional, right? That's how we say, right? But we would rather say multi-stable. But then you have to define what stability means in this case, right? or how they would say in neuroscience, they would say multimodular, which means it has multiple modulus. Okay, so is it, or some circuits are not meant to be multi-stable. They have to produce one particular rhythmic outcome, again, as I said, in sea slugs, which should be swimming, but they have to do this over and over again in million species, right, where the neurons have huge deviations in individual parameters, but the network still made of chip elements kind of robustly produces the same rhythmic outcomes. Okay, like again, the swimming, that's the very first image that I picked, right? You see, it's just swinging back and forth, right? Flipping back and forth. But interesting enough that the same animal, when it's small, right, it brain knows that this swimming frequency must increase to produce the power or that propulsion strong enough for the animal to swim. Okay, but when animal gets older or the body it becomes larger, then the swim pattern frequency drops down, and it's a much slower on the order of magnitude. And imagine that if you if you warm up the water, the animal is not going to swim any faster, but it still produces this rhythmic outcome, which you may say it's a simple and primitive, but it's not that simple really, right? Okay, so I go back to this slide, and what we are trying to do, in particular in my lab, this just we just had a paper published on this particular circuit. This is called a toy circuit. So basically, we sat down and had a conversation, unfortunately not long enough to discuss what's called in neuroscience the model. In neuroscience, model is not a system of differential equations. In neuroscience or in biology, or typically a model is a concept. Do we need this connection, an inhibitory? That looks like we need inhibitory connections because we want to produce antiphase, but we also add up excitatory connection, right? Because again, in this case, as you can see, these poles move in phase, right? Which means, depending on the drive, if the drive is, say, low enough, then these two cells should fire burst. I mean, we're going to talk about bursting later on in phase. And then when drive increases, then they start firing in antiphase. So which means we have to take into account not only the drive, but how the drive affects the interaction, the coupling between the cells, right? So which means, say, excitatory synapse activity must be stronger at low drive, and then it should be replaced by inhibitory connectivity at higher drive values, right? So to switch to, say, to trout from bound. So yeah, these are still interesting questions, and these are modeling studies, and the truth is that nobody really knows whether the circuit should be like that, right, which is minimalistic circuit, or you should add the extra elements. But again, every time you have to argue why. Okay, there must be always a reason why you would like to propose or add up this connection, how it's going to affect. That's what's called modeling. You propose concepts, and then you try them out to see how it works. Okay, and again, the truth is that don't expect any mathematically rigorous proofs in this department. Okay, in this department, in this kind of line of research, you don't prove, but you demonstrate and you articulate and argue why this is true, right? And if it's true for that particular circuit, it can be generalized for other circuits. So you can see universality of the principles. So that's what you're supposed to do. And I showed you that slide before, but what we're going to do next is we're going to talk more and more about what's called chemical synapses. That chemical synapses in neural circuits, they, I don't want to say they play a more important role than electrical gap junction. It's not true. As I said, electrical gap junctions need to create clusters of cells, okay? So which means sometimes one cell on the network, its contribution could be minimal. But if you have, say, 5 cells coupled by gap junctions, then it's already a chorus of cells, right? It's already a cluster of cells, and they can be heard better and their contribution in a network to the network dynamics can be more articulative. Okay, so and the other thing is that you should know. I mean, again, it's just a story from neuroscience textbooks that just I mentioned it last time that Native Americans, Indians, they used curaria, which is neurotoxin extracted from the juice of particular trees, and that neurotoxin, they again empirically they found it, right. Apparently, okay, I don't want to go into that stuff, but apparently they found that if you happen to drink it, right, or I mean depending on the concentration, right, then you no longer move, right. Somehow it affects your locomotion properties, right. So which means it destroys the coordination between the cells that would produce this kind of activity. Okay, so I'll just give an example. This is one of the examples that I really like, and in my mailbox, I have an inbox and I have folders, of course, right? And then I'm going to open up this email, click on the picture. Okay, you saw this animal is called Melibi leonida. It's a sea slug. Okay, and that's how it swims. And neurophysiologists that I used to collaborate with, right? We still collaborate, but not that intense anymore. They demonstrated that they found cells in the brain of this animal that is called interneurons. They're part of the CPG, okay, and that CPG during the swimming episodes, the cells produce this rhythmic outcome. Okay, you can see, okay, burst of activity followed by this burst of activity, then there's some kind of delay over here, right, and so forth and so on. Okay, so in particular case, these cells, SI1 and SI2s, they're coupled by strong electrical gap junction, which means these cells fire together. So you don't have to consider them separately, right? They fire together. And then Akira, I mentioned his name several times last time, right? He applied what's called TTX. TTX is another neurotoxin, neuroblocker that found in a fuga fish or in a boilfish in Japan. Very, very popular and delicious fish. And the cooks, chefs that prepare the fish, they know the physiology extremely well. That's why they have a license. Okay, as I said, that certain organs in the fish are highly poisonous. They contain these TTX. And what happens to humans when they consume the fish, right, and consume the liver of the female fish, then the TTX, as I said, goes into the stomach, then in the blood, and then it basically delivered to somehow, again, don't ask me, nobody knows this, right, and I don't know that either, to the circuit that controls the breathing, right, and it decouples the cells, it's called respiratory center, and the cells no longer function, right, and then the human stop breathing, right, and needs artificial breathing enforced. Okay, so in case of this animal, when Akira applies a little bit of TTX over here, okay, then this pattern that is stable and well pronounced becomes something like that. Okay, so which basically that factor proves to us that in isolation, none of the cell is what's called endogenous burster. So they're just tonic spiking cells like integrated and fire cells. Okay, and that's what you can see. You can see little episodes, right, of bursting, but apparently still TTX either not strong enough, so it doesn't disconnect the cells from each other. And by the way, what also I guess I mentioned that time. Meanwhile, what Akira does, he records from the cell. You see these electrodes, and then using the computer, he generates what's called synaptic current, that we're going to talk about this now. Using the spikes, it generates synaptic current, and then that synaptic current is injected into this cell and vice versa. And as you can see, he partially restores the swinging pattern as it existed in what's called control case, okay? So, but he also restores only the swinging pattern between these cells, okay? So they produce anti-phase bursting, Si3s, right? They're still tonic spikers. And this raises multiple questions. Why you need these cells, right, in a network to produce this pattern? Because it looks like the pair of Si2s should be enough to produce, you know, this pattern, swinging activity of the cell in the cells. So there are tons of interesting questions. So let's address how we model in inhibition. Okay. So the biggest question for us, for me, and it's still a big question for modelers, is that models of synaptic currents are quite primitive, and nothing wrong with being simple models. When I say primitive, maybe I picked the wrong term. Nothing wrong with being simple, but they are not good enough often to deliver what we expect in the numerical experiments. Okay, so they don't answer the goals that we set for them. Okay, but in simple terms, right? Whenever you have cell number 1, cell number 2, and whenever presynaptic cell, blue cell, generates an action potential, if you have an electrode in a cell on the right, then you will see something like this, right? And it's going to be around 5 millivolts, and you will say, hey, this means this is inhibition. Okay, that's why the spike causes what's called hyperpolarization in a driven on postsynaptic cell. Otherwise, if you can see these little bumps, then you would say this is excitatory postsynaptic potentiation. That's how Akira determines, okay, whether the synapse is inhibitory or not, right? And this basically shown over here. Whenever the blue cell generates a train of spikes, it causes this zigzagging in the red cell on the right, which basically means that you see the cell tries to wake up, and then this pulse pushes it back down, right, and say, this is inhibition, okay, wait for me until I finish, okay. And what you see here, and I already mentioned that last time, but that was 1 week ago, very likely you've forgotten that, these are real recordings, right, and then we try to blend neurophysiology and mathematical modeling. So we are trying to figure out how this biological bio-neuron communicates to the other cell of the network. And what you see here, and that's why you have spikes in these cells, whenever the cell fires a spike, it releases what's called neurotransmitter, which is basically a messenger, and that messenger goes towards the other cell, right? And it basically tells the other cell what the primary or the presynaptic cell wants to say. Okay, and all it wants to say is like, be synchronous with me, or please be patient and wait until I finish producing this burst of activity, and so forth and so on. So that's what we're trying to figure out, how they may possibly interact. Okay, so, and the very simple model, okay, so we need to create a model that's called neurotransmitter rate models. Okay, it's basically a probability of releasing neurotransmitters, and the idea in the chemical synapses, unlike electrical synapses that always interact, there is always current between two cells that are coupled by electrical gap junction. These guys, they have a threshold, so it's kind of one-way communication. So as long as the cell is below a synaptic threshold, it doesn't talk to the other cell of the network. But as soon as it reaches synaptic threshold and it generates spikes, then group of neurotransmitters will reach out the postsynaptic cell, right, to deliver the message, okay? And the simple solution would be just to use a heaviside. So as soon as the voltage, okay, this function, which is the probability of release of neurotransmitters, okay, or depletion, if the voltage is less than synaptic threshold, function probability is 0, otherwise it becomes 1. Okay, it's straightforward, simple. Okay, 0, 1. Okay, simple as that. But I'll also mention that Heaviside function is, first of all, it's too sharp, right? Which is kind of unrealistic. So you better have a kind of smoother version of that Heaviside function. And this is called sigmoidal function and also logistic function. So that's how the function looks like, right? And I mentioned last time that some people use inverse tangent to generate this kind of graph, or you can use hyperbolic exponents to generate basically the same thing, right? And we're going to use that notation in the future, right? So, and the point is that as soon as voltage below certain synaptic threshold, probability is almost 0. Otherwise, it's going to be 1. And you can control the shape of this graph. You can make it very steep like this if you change this number and make it say 100, right? Or you can make it smooth, right? So there's always some kind of neurotransmitter release on the background, so it never ends up, and then it reaches some kind of maximum at higher voltage values. Okay, so that's what we need, where we are. Okay, and what I was trying to tell you too is that the way it's modeled is whenever neurotransmitter reaches the presynaptic cell, it knocks on the door, knock, 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 right, and let me in, but it doesn't let, neurotransmitters don't go inside the cell, right? All they do is just let the other cell that open up that gate, so and release a positive ions from your interior, so which means voltage goes down, or vice versa. Okay, let them in, so the voltage goes up, so it generates the spikes. Okay, so and basically it may cause what's called activation when the gate opens up inwards, right? Or it can cause inactivation when this gate is supposed to open up, not inward, but this is outward, this is inward. Okay, so different options. Okay, this is called activation. If voltage increases, the probability increases, otherwise it decreases. Okay, so go next. Okay, and the other approach, okay, this is called FTM, I mentioned last time, right? You use this function, this is just algebraic equation, and basically the sigmoidal function either 0 and 1, but it's smooth interpretation, right? And basically what you will see that as soon as spike above synaptic threshold, you're going to get that probability that is 1, otherwise it will become 0. Right, then the approach that we developed further is we use what's called dynamic synapse, and the first model of dynamic synapse is called alpha synapse. It was proposed by John Rinzel, and the idea he was inspired by his I don't know, his advisor or his a mentor who was neurophysiologist, who actually was first to propose that the probability basically given by this function known as mathematics as an alpha function. So first of all, as soon as you reach the threshold, there is a little delay, and then neurotransmitter rate starts increasing, and then spike goes down, and then neurotransmitter release rate decays, it goes back to 0. Okay, and again, it's inspired by Hodgkin-Huxley formalism, and it's a simple differential equation basically that control this alpha synapse. Okay, so this beta term determines the convergence rate, right? And alpha basically is in charge of that initial increase profile. Okay, so we talked about this time, so let's speed up a little bit. Okay, I'll skip this picture. So basically, I mean, all I'm going to say is that for us, it's very important that the probability, average probability, is a function of the frequency in presynaptic cells. Okay, and that's what we need. That's our model of the dynamic synapse. So when frequency is relatively low, then neurotransmitters the probability is not 0, but again it's small. And then when frequency is high, probability is almost 1, and that's how the cell should interact, right? The interaction should be flexible, it should be controllable. Okay, that's basically the message of this slide. Okay, and this file, integrating file alpha synapse, okay, basically shows you what you can do. So there are two panels. Okay, so one the 3 panels on the top, is integrating via, you inject a current 6 nanoampere, so it gives you a number of spikes here. Okay, that's what FTM should give you, right? Basically give you these poles of neurotransmitters reaching this value of 1, where the alpha synapse is going to give you a kind of continuous, I mean, it's continuous to you, but a smoother version or average version of this, right? It doesn't build up as quick as, and then it converges like that. And then when you inject a higher pulse, like 10, then the frequency in a presynaptic cell goes up, and this would be how alpha synapses will control the probability of neurotransmitter release rate. As you can see, as frequency goes up, then FTM approach gives you narrow pulses because frequency is higher, which means this synapse gets weaker as spike frequency increases in presynaptic cell, but we require the opposite. Okay, so that's the file in a Dropbox. You're welcome to upload it and then run it and change just this number. And also I do suggest that keep this alpha number fixed intact, and you're welcome to play with beta to see how beta affects the neurotransmitter release rate. And the overall idea is that if you make this beta smaller, right, which means that convergence is going to get not as fast as it used to be, right? It's going to be something like that. And it doesn't reach 0 when the next spike arrives, and it's going to stay above certain level, right? Which again is going to make the synapse stronger as time, as the frequency increases. Okay, so synaptic currents, how we model synaptic interaction. So we introduce the synaptic current, right, in addition to external current. Again, historically, don't ask me why, but historically, synaptic currents always have minus in front of them. And the idea would be the following, right? If say, the postsynaptic cell wants to generate exponential, something like this, right? Something like that. And then synaptic current gets into the cell, it will accelerate the spike. It's going to speed up the spike formation in a cell. Otherwise, okay, if synaptic current is negative or inhibitory, it's going to delay the spike formation in a cell, something like that. As simple as that. How do we model that? We see this equation, V prime. Okay, V prime is supposed to increase. Okay, so basically, if I want to speed it up, I need to add a term over here that overall is going to be positive, which means I will increase the rate of change of V. Okay, so which means synaptic current model as follows, right? So you have this weight, which is called, again, maximal conductance, right? This number can be, again, it should be reasonably peaked, right? Define what reasonable is. It depends on S. S is probability. S probability, which means it's between 0 and 1. And then you have voltage in the cell, and then you have what's called synaptic threshold. Okay, not synaptic threshold. It's this level, reversal potential, determines whether inhibition is going to be positive, or whether the synaptic current is going to be inhibitory, okay, or excitatory. So again, if I want to make sure that this expression is positive, okay, Gmax positive, S is positive, right? I want to make sure that this difference is negative, which means V seen should be higher than V. So which means, okay, I want to make sure that I place this reversal potential above the spike limit. So if this is 40, it's got to be around here, okay? Otherwise, if I want to model inhibition, I want to make sure that okay, I preserve the negativity of the sign, okay? So which means I want to make sure that that difference, okay, overall stays positive, which basically means that I'm going to place the level over here at negative 90 millivolts for inhibition. Otherwise, it's going to be up here above spikes. So to make sure that this difference either positive or negative, as simple as that. And again, this is one kind of concept. The other concept that you should see is that, okay, as I said, you want to make sure that when synapse is excitatory, you always see that bump over here. Okay, otherwise you're going to get a hyperpolarization caused by this train of spikes. This means inhibition. Okay, or if you have a spiking cell and that cell gets excitation, then spiking rate should go up. But if it gets inhibition, then spiking rate should drop down. Okay, click, click, click. Okay, here we are. Now we're getting back to the same file, right, but this time it's called integrating file realistic 2-cell with phase lag. So the difference between the previous file is that the previous file has realistic 2-cell electric phase. So this one doesn't specify. And what you see here in this particular case, right, in this file, so you have integrating fire cells. You can change, and that was basically a drill for students in the classroom to see how different beta values change the interaction between the cells, right? And you're welcome to do this too. Okay, this is maximal conductance. I keep them equal. And then 2 lines over here. As I said, if you make reversal potential high enough, 70 above spikes, right? So these spikes reach up only up to 50 millivolts. Then if you keep this at this level, right, the synapse is going to be excitatory. But if you move it to the level of negative 70 over here, then your synapse is going to be inhibitory. Okay, so we can see that these 2 examples. Okay, so what I've done here, our peak initial conditions to emphasize that the cells from the very beginning, they're kind of in anti-phase. You see a phase difference between the blue and red, and my blue cell is a reference cell. And as time progresses, you see that the difference, the delay between the spikes goes to 0, okay, which basically means that the red cell kind of accelerates and catches up with the blue cell, so the phase lag goes to 1. Okay, but if I change this number to negative 70, then typically, right, I'm going to see this, right? So if the cell, actually no, this is just excitatory cell, I'm sorry. But this time, okay, blue followed by red again. As you can see that the phase difference now goes to 0, which basically means that it's just illustration what modulo 1 means. In both cases, you argue that very likely, not very likely, because you do know that you set up the threshold, that the network is excitatory network. Okay, and in contrast, in this case, when I use inhibition, I use negative 70. Cells that start off almost together as time progresses, right? You see they go in anti-phase. So that's what you see, the phase difference, phase lag converges to 1/2 or vice versa like this. So that's how you model inhibitory interaction between the cells, okay? And tell me the difference here. I have no idea what the difference. Oh, okay. So again, this is just a wrap up what I've just said, that the level, this level, whether it's negative 70 or plus 50, right, determines whether the synapse is going to be inhibitory, in this case, or it's going to be inhibitory again in this particular case as well. Okay, so maybe I used too many slides to emphasize the same story. All right, so there's another file in a Dropbox. It's called integrating fire. It's called exponential and bursting 2 cells. Okay, I mentioned before that in general, okay, that integrating fire neurons are not meant to produce this kind of bursting activity, but there are tricks that you can use, right, just to make sure that these pulses of current, they kind of keep up and going. So this basically this kind of getting variables. So basically this controls that if certain variable goes up, then generate exponentials, right? And then if that getting dynamics decays, then integrating fire cell become quiescent cell. It just kind of mimics the bursting behavior. And in this case, I'm using excitatory synapses to couple these two blue and red cells. Again, it's controlled by the level of the reversal potential. And as you can see, not only spikes, but typically the burst of activity will become synchronous if 2 cells are coupled by excitatory synapses. Otherwise, if you use low level of reversal potential below snappy threshold, like negative 70, right? Likewise, spiking cells, these bursting cells, you see they're fire in interphase, right? Okay, and also very similar to we talked about before, right? Okay, so the fire in interphase. So where am I now? Okay. Again, you try. I mean, you're welcome to play with this file, but again, we're gonna use it in the future, right? Okay. So then I go back to this two distinguished gentlemen, Alan Hodgkin and Andrew Huxley, who developed, again, they developed what's called certain formalism. They invented what's called gating, voltage-gated channels, okay, in the of the cell. So what it's supposed to mean? So let me find that file if I see it here. Oh, the picture. Let me see it. Where is it? Yeah, here we are. That's what they invented. So basically, they said that all these currents, sodium, potassium currents, like pulling Kirchhoff law, a current is a difference between voltage inside the cell outside. It's called cross-membrane voltage, divided by basically by divided by the resistance of the gate, or say resistance of that membrane. It's not totally true because this membrane is capacitance. So basically it's a V1 minus V in interior minus V exterior divided by R. Then we replace R by maximal conductance. But what they, Hodgkin and Huxley proposed, they said that this current is a function of the voltage, cross-membrane voltage. So they multiplied that current by a probability. Okay, in this case, N or M or H, these variables, okay, their probabilities between 0 and 1, and basically meaning that if probability is 0, the current non-existent. If probability is 1, the current is fully maximized. And of course, there are intermediate values. So their gate is slightly open, but still ions can sneak through that gate, right? So which means current is not strong enough, okay? And strength of the current is determined by the maximal conductance. That's what Hodgkin and Huxley proposed. And let me just show you. I go back to some simulations. I click here, and then click, and then I go to this file, Hodgkin-Huxley directory. It contains a single file. It's called Hodgkin-Huxley. We're going to talk about this more, right? I will explain how it works. But at this point, all I need to do is I just click and say run. Change the folder, run it, and where is the file? Yeah, it's right here. Okay, and as you can see, like, is it? Yeah. Yeah, it says membrane in time. Yeah, no, I don't like that. Do I? Let me see, do it again. Run it. I wasn't quite sure. Okay, here we are. So you see what my confusion? Okay, my confusion was that before it looks like it's an integrating file. If you don't see it well, let me just come over here, and then I'm gonna subplot. Okay, let me do this. I'm gonna add a couple of lines, and okay, comma, and say line width. Okay, and I'm gonna make it 2, and then I copy and paste it over here. It says plot, and then edit, and then okay. Let me see if I run it again. Oh, I changed that legend. That's kind of funny. Oh, it's X label. Oh, Jesus Christ, I put it in the wrong place. Remove this. Okay, keep it here. I mean, we don't need it here. Can you see plot? Yeah, it's right here. Plot, I'll put it this. Remove the second comma. And okay, run it again. Now you can see I changed the length, line length of this plot. And where is the first one? It's right here. Okay, I changed it here. So you better see what's going. Oops, unhappy because I have 2 commas. Okay, run it again, and now you can see the spikes better. And there are multiple numbers that it's called conductances for the, you see there's crazy numbers like maximal conductance for the sodium channel, right, 120. All these numbers come from experiments. Okay, the only, again, the only bifurcation parameter, okay, let's do this and call this bifurcation parameter in this case, is the external current, which is 7 in this case. And what I'm going to make it like 4. No idea. Let's see what's going to happen. If I do 4, as you can see, that initial conditions are picked so that the Hodgkin-Huxley model generates an action potential like this, and then it converges to the rest potential. In this case, it's slightly above than 60 millivolts, right? And you can see it even kind of oscillates towards the rest potential. Okay, so let's play the game and make it 4.5. All right, how about 9? I just want to make sure if I see a better oscillations in the system. I can't convince myself that I see better. I'm going to make it 5. Okay, first of all, I'm not quite sure if the picture changes at all. Let me see. I'm going to put something like this. CLF. Let me do. Oh. Okay, I'm going to close it, run it. Yeah, looks like it's the same. It's the same thing. Okay, I make it 6. Yeah, I can see the changes now. You can see oscillations, right, converging to the steady state. And I'm going to make it 7. I should see spikes. Okay, what if I do 6.5? Okay, let me just play with this 6.2. Okay, I want to make sure that I want to find the threshold. Okay, threshold for, do it again. Okay, I can see better oscillations. That's why we need to understand better how oscillations emerge in the neural models or in any kind of models. Just let me see if I do 6.6. Okay, so they quickly emerge. Okay, sorry guys, I know I'm playing 5. How about 45? 45. Okay, 4. Oops. Okay, this. Okay. 4. All right, enough. Good enough. But it's very interesting what you see here, right? The current is strong enough to produce 3 spikes initially, and then like a pendulum, this oscillation cease and converge to the steady state. So, but you see the oscillations. So if you think of the steady state, how it's going to look like, right? Then very likely, if I compute the equilibrium state in the system and I compute the eigenvectors of the linearized matrix, I should get complex conjugate eigenvalue with negative real parts, and so I can determine what the imaginary part is, right, and how quickly it converges, what the negative real part should be, and so forth and so on. So we found this value. Just let me keep it. I'll just make sure that I'm on this edge, and then I'm going to make this number say 150. So what we will see. Okay, so you can see it still converges some steady state, but this current is strong enough. Let me find some intermediate value, 15. So I can see action potentials, but the difference between the previous value, 6, and this one is, you see the different level that these oscillations converge to. If I make this number crazy enough, 170, the current, then as you can see, this level is above negative 40, whereas if I make the current low than the initial value, that level is negative, close to negative 60, which basically means that the cell has potentially 2 steady state at different current values. Okay, when current is 6 around this, right, we say that the steady state or rest potential is hyperpolarized, it's around negative 60. Whereas at this, when the drive is strong enough, then it's above negative 40, right? This is called depolarized state. So there are like 2 levels, right? before you always converge to a low level. At this drive, you always converge to a higher level. And that's important for our future consideration, right? For our future modeling. So that's what Hodgkin-Huxley model is supposed to do, okay? And basically what you see here is these are just dynamics of the gating variables, the channels that determines the overall dynamics of the system. As I said, we're going to talk about this later on. So at this point, I close this file, okay, and close that, go back to my lecture. And what time is it? Is it, so I talked for 1 hour and 20 minutes. Should we get a break at this point? I don't remember. Is it 1 hour and 20 minutes and then 10 minutes break? Hello?
Yes. Ну, так нужно делать, да.
Okay. All right. So, I mean, what I'm trying to say is that what you see here is a Hodgkin-Huxley type of cell, right? That's what it produces, different kind of dynamics. And as you can see, this is oscillatory dynamics. So that's why we better understand what oscillations means. And that's why I got to this next slide over here that basically wraps up certain historical indicates certain historical comments in development of the oscillatory dynamics in individual cells. Okay, now we are going back to individual models of neurons, oscillatory cells, and what models we use. Okay, and okay, let's take a break. I need a glass of tea too, so I can warm up my throat. So we'll continue talking in 10 minutes. All right. Okay, see you in 10 minutes. Okay, I can turn the video on at this point, so you know